Hello, this is Dr. Strickland. In this video, we will investigate the nomenclature of cyclic carboxylic acids, lactones, and lactams. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So if you have a carboxylic acid group or a carboxylic acid derivative that's attached to a cycloalkane, then the cycloalkane gets to be the parent. And so in this case, we'll have a 5-membered ring. Think about the name of that. And then here, we've got a 4-membered ring. And you can see we've got some stereochemistry to take care of. But in both cases, the entire functional group is outside of the ring. And, you know, carboxylic acid groups can be written like this or like that. So I wanted to show you, remind you that that's the case. But with acyclic carboxylic acids, that carbon right there is not only part of the functional group, but the first carbon of the parent. When it's attached to a cycloalkane, it can't serve in both positions. And so that's why decisions have to be made. So this guy is called cyclopentane carboxylic acid. Okay. Now over here, we'd have cyclobutane carboxylic acid. But you can see that there's more to it. Okay, so let's see. First of all, we need to number this thing. Carboxylic acid group is a group of highest priority. It's higher than the methyl. So it would have to be 3-methyl. And I'm just going to put a hyphen since if I put it there, it's going to get scrunched because we need a little room for the stereochemistry. And you can, since it's a cycloalkane, you can either do the R and S configuration of both. Well, let me ask you a question. Can you do R and S? Are these asymmetric carbons? They are not, because the path around the ring is the same. But you can say that it's cis. Okay. All right, so cyclic esters and cyclic amides very often have the functional group as part of the ring. And the most famous ones are ascorbic acid and erythromycin. And so over here is ascorbic acid. You know, that's just vitamin C. And let's find out what we've got here. See, with these 5 members of the ring, you can see one of them is actually an oxygen and one is a carbonyl carbon. And here is the ester right here. Okay. 5-membered ring, ester here. Over here with erythromycin, we can do the same sort of thing to find the ester. It's called a macrocycle because it's so big, but you can see right here, there's the ester, and it is fully part of the ring. How many atoms are part of this ring? If you count all the way around, how big is this? Okay, so I want you to pause the video and find out how many atoms are in this cyclic structure, and then come on back. Welcome back. So, you know, ascorbic acid is a 5-membered ring. But erythromycin, if you said it was a 14-membered ring, you would be exactly right. And you can see that when people did the synthesis of erythromycin, they had to go for one stereoisomer that had all of these different asymmetric carbons on it. And you can calculate, you know, the the maximum number of stereoisomers you could have for a connectivity with this many asymmetric carbons, and to just make one is a pretty impressive feat. So if you're going to name lactones, their names are actually related to the names of ketones, and we haven't done ketones yet, but we can certainly take a look at one. This is a ketone. We've seen acetone and a few other smaller ones. This is called cyclohexanone. And we'll do the nomenclature of ketones in time. But, you know, it's the name of the cyclic parent plus ONE. And the ONE replaces the final E on the parent. So if you have an oxygen as one of the ring atoms, you're going to number this so that the oxygen is atom number 2. And this is one of those rare times when atoms other than carbons get to be part of the parent. So what we call this is 2-oxa cyclohexanone. And then similarly over here, let's number it. The oxygen gets to be atom number 2. All right, so I want you to pause the video and write the name of this compound and then come on back. All right, welcome back. So you can see it's a 2-oxa cyclopentanone, and it has a couple of methyl groups attached to carbon 4. So if you've got 4,4 dimethyl 2-oxa cyclopentanone, you are correct. Good job. All right. So lactams are cyclic functional groups also. In the same way that a lactone is a cyclic ether, a lactam is a cyclic amide. And probably the most famous lactam is the reactive center of a penicillin molecule. And if you think about when we talked about ring strain of cycloalkanes, you think about how much ring strain there is tied up in that little 4-membered ring. It is no wonder that one of the main things that molecules like this do is to open right here. And then actually this goes in, we'll go and take a hydrogen. Let's put a hydronium ion in here. But if you've studied any about penicillin, you know that there are a number of varieties, a number of different kinds of penicillins that vary with the identity of this R group here. And you can see that it's, you know, this group that has to do with the cell wall of the bacteria that opens the 4-membered ring here and makes it impossible for the bacteria to form their cell walls. Okay, so the names of lactams are very much like the names of lactones, except that we use aza to indicate a nitrogen at the 2 position instead of an oxa to indicate the presence of an oxygen. All right, so that is the basic story on cyclic carboxylic acid derivatives. If you have any questions, please send them to me.